What's up, guys? It's Mr. Schwanenkamp. Today we're going to talk about Doodle Notes, chapters 4 and 5. Doodle Notes is not going to be as important since you're at home. Normally the whole idea with Doodle Notes is that way you don't get bored with me. You could draw a cool little picture, but you're already away from me, so you shouldn't get too bored. I'm going to go through these pretty quick, just to remind you of each of the topics. I don't have area and volume on it since we just tested over that. We'll do that later on. But we're going to go through two different things. We're doing integration and then differential equations and some U sub in there as well. So we'll talk about those two things today. Not a specific assignment to attach to this besides working through the semester 2 packet. But let's see how we do. All right, so we are talking integration here. And so one of the first things we really talked with integration was average value. And so when we see average value, the thing I'm always going to say to you is if I wanted you to find the average of your test, okay, if I gave you 3 test scores, you got an 80, a 90, a 100, and I asked for the average test score, what would you do? Well, I'm guessing that if you were trying to find the average test score, you would take those 3 scores and add them up. That's what that says, I swear. Add up, and then divide by how many you got. Very proper. Divide by how many. All right, so by doing that with calculus, this is what you're going to do. So we are going to integrate from some number to some number. We're going to add them all up from A to B. Okay, we're going to add up whatever we're doing. So if I did velocity via TDT, we're going to add them all up and then divide by the difference, B minus A. What would that find you if I took velocity, solved it from A to B, and then multiplied by 1 over B minus A? That would find you the average velocity, because whatever I am taking the integral of is going to be what I'm finding the average value of. Okay? So, example here, the temperature F of a cup of coffee, T minutes after it is poured by F of T, what is the average temperature? So again, they told me temperature. I want to know average temperature from 0 to 10 minutes. So to do that, I would integrate from 0 to 10, F of T. That would tell me the total temperature. Doesn't tell me a lot. Okay, if I add them all up, it just tells me all of the temperature degrees. So if it was 50 degrees and 60 degrees, or when I guess it would count down 80 and then 70 and then 60. If I just did that, it would tell me 80 plus 70 plus 60, which doesn't do me anything. Okay, instead, I want to take that thing and divide by however many minutes I went. So here I went 10 minutes, so I'm dividing by 10 minutes. You would take that, plug it into your calculator. You would get 148.2, I'm sorry, 0.820. And we started with this measurement. So it's the temperature of the coffee. I'm going to guess in Fahrenheit. So it's going to stay as degrees Fahrenheit. We started with temperature. We found the average temperature by adding them all up and dividing by however many we had. Next thing we did was the derivative of an integral, and that is FTC. Okay, so this is a specific part of FTC. We do FTC all the time, but this is a specific part when you take the derivative of an integral. So it looks like this. This is what I'm deferring to when I say take the derivative of an integral. We've got an integral going on, and we're going to take the derivative of it. And so it is equivalent to squaring a square root. Well, if I square a square root, those two things are going to cancel. If I take the derivative integral, they're going to cancel, kind of. Okay, make sure x is in the upper bound. That was a key. We're going to plug in that upper bound and then multiply by the derivative of the upper bound. So for example here, we've got 3x squared. So 3x is in my upper bound. I want that up in my upper bound. I'm going to take this and plug it in. So my problem is going to look like this. E to the 4 minus 6. Everything there is going to stay the same. All I'm going to do is take that 3x squared, plug it in for x, or in this case t, and then I'm going to multiply by the derivative of what I plugged in. I plugged in 3x squared, and so the derivative of that would be 6x. That right there is going to be my answer. Okay, it's a little bit funky. Just again, something if you memorize, it's easy. Make sure you can do it. Next thing we're talking about is RAM, and just trapezoidal sums in general. Breaking up a function into parts and selecting either the left, middle, or right value. That is what RAM represents, rectangular approximation method. Okay, and so we're going to choose either the left side, the middle, or the right, just depending on the problem, and we are going to use that to find the area under the curve. So we're going to use the left, middle, or right value, and then multiply by the width to create the area of a rectangle. Rectangular approximation method, that's what it stands for. To approximate the area under the curve. That's what we were doing with this. We did this a lot of different ways. We could do LRAM, we could do trapezoidal. They might be split up evenly, they might not. So this one is not. And so if I'm doing LRAM, all right, and I wanted to figure out what the area under the curve was from 0 to 50 of whatever this function is, of f of x. Okay, I could approximate that with LRAM. This isn't going to tell me the exact answer. It's going to tell me an approximation. But remember what we do here. We're going to make our little lines. I would strongly suggest you connecting the boxes. So I'm going to have 3 different intervals. I've got 4 numbers. It's going to get me 3 intervals. I'm going to figure out what is the span across the two. So it's 25 across times. We're doing LRAM. So LRAM would be the 4. Then we're going to do the next one. The next one, we're going from 25 to 30. And so I'm spanning 5 across times whatever my left number is, which is going to be 6. And then we got one more. We are going 30 to 50, so we are 20 across. And then we are going to multiply by the left number, which would be 8. We take all of those numbers, we multiply them together, and that would get us LRAM. Okay, LRAM, not too bad. Trapezoidal sum, that might be one you forgot. But trapezoidal sum, remember, it's exactly the same. Okay, it's still going to approximate this. It's going to approximate it better, but it's still an approximation. To find trapezoidal sum, all we're going to do is take the width times the average of these two things. So 4 plus 6 divided by 2. So 10 divided by 2. Oh, it's like times 5. And then we do the next one. My next one, well, how far apart I am? I'm 5 apart. I'm going to take the average of these two numbers. 6 plus 8 divided by 2. And then my last one here, we're going from this one to this one. Let's keep color coding. We are 20 across times the average of these two, 8 plus 12 divided by 2. That is trapezoidal sums. Not too bad. Then we've got area under the curve. And so this one's easy. This is an F graph. G equals the integral from 2 to x of f of t. All right, so think about that. G is the antiderivative of f. So in other words, if I had f and I went backwards, I would get g. So we could call this a graph of g, or in other words, we could also call this a graph of g prime. G prime, that's a key here. So if I want to find g of 0, I've got g prime. I want to talk about g at 0. That is the area under the curve. Okay, area under the curve. So to find g of 0, all I'm doing is taking this equation right here. I'm going to plug 0 in for x. So I'm going from 2 to 0, f of t dt. So I'm going to find the area under the curve starting at 2 and going backwards to 0. Since I'm going backwards, it is going to be a negative area. The answer is -4. That is this area right here. That's what we just found. It's -4 because we're going backwards. Then we're doing g prime at 3. G prime, oh, this is a g prime graph. G prime at 3, oh, that's easy. I'm looking right there. Boom, the answer is 2. Okay, don't let that one be tough. G double prime at 6. Okay, so I'm going to 6. I'm thinking about G double prime. This is a graph of G prime, so what am I going to look at to find G double prime? I'm looking at the slope The slope of this graph at 6 is +1. I'm done. Let's go to everyone's favorite series notation as an integral. A quick reminder of how this thing works. All right, this is the little formula that we've got to work with here. And again, just a couple things to point out. We are going to include the width in our problem, whatever our b minus a is. So that's my upper bound minus my lower bound divided by n. And so we're going to have this b minus a over n concept in my problem. And then I'm also going to have the right side, and that's a plus b minus a all over n. So it's a little bit funky to look at, but let's do an example here, and I think it should make more sense. My width is going to be 3. 3 minus 0, that is 3. And we're going to take that and divide it by n. So which one of these has 3? Not that one. That one's got a 3n. That one's got a 3n. Not that one. Okay, so that's the first thing I'm always looking for. I'm looking for the width. Once I've found the width, I'm going to then think about the height. Okay, so what would the height be? Well, the height is going to be what you get when you take the width and you plug it into your function, starting with your starting value. So 0 plus the width times I. Well, my width is 3I, which is this guy right here. Boom, that is the right answer. That one right there is funky. You might want to take a minute and go back and look at some Khan Academies over that. Probably not the most important. It's going to be one multiple choice question. That's it. That's what it'll be on the AP exam. I'd love for you to be perfect at it, but if you're not, we'll live. Antiderivatives with no bounds. Just remember how to find an antiderivative. 2x to the 3 halves. Remember, if it's no bounds, plus c. Let's find an antiderivative. We are going to add 1 to my exponent. So x to the 5/3. And then I'm going to divide by my new exponent. So if I'm dividing by a fraction, I'm really multiplying by a reciprocal. And then do it again. Ooh, 3 times, that's like 1 over x. So the 3 is a constant. What is the antiderivative of 1 over x? That is a natural log of x in absolute value signs. Don't forget that. Plus, I'm sorry, the antiderivative negative sign. So snap, chat, negative, snap, chat. We are here at negative sign. We work backwards. Oh yeah, it is a positive cosine x plus c. That is my answer. Obviously, 3 times 2 up here in the front. We could make that 6/5. But other than that, there's my answer. Just straight antiderivatives. Make sure you can do it. One more here. I think I'm going to cut this video into 2 parts just because. Antiderivative with bounds, so we're going to find the antiderivative, capital F of x. The antiderivative 4x squared, add 1 to my exponent, divide by my new exponent. Add 1 to my exponent, divide by my new exponent. We would go plus c, but we've got bounds. So remember when we got bounds, it's -1 and 2. We're going to plug in 2, so 4/3 times 2 cubed minus 2 times 2. Then we're going to subtract this whole thing by plugging in -1. So 4/3, -1 cubed minus 2 times -1. Make sure we put that all in parentheses. If you want, you can simplify that down. For the sake of my own sanity, I'm going to just get me an answer here of 6. You can do that math. So antiderivatives, remember, no bounds plus c. If you do have bounds, we go upper bound minus lower bound. That's the key to success. That is antiderivatives, more specifically talking about integration. Those were our first 2 chapters of the semester. Part 2 coming up.